Everyone, today we're going to be talking now about band diagrams, which is a very useful model for describing the properties of various materials, and as we're going to discuss, semiconductor materials. And then also these models are very useful because then we can figure out ways to take advantage of these properties from these models for engineering use cases. So we're going to start off by talking about a model that we should be familiar with already, which is the atomic model for any atom. So for example, we're going to use the example of silicon in this case, right? Here's a picture of the silicon atom, and it has the electron structure. It has an atomic number of 14, which means that it would have 14 electrons, right? And we can figure out the shell structure for it by writing out the different orbitals, 3s, 3p, 3d, and then counting out how many electrons there are in each orbital. So there's 2 electrons in the 1s, 2 electrons in the 2s, so that makes 4, and then 6 in the p1, so that makes 10, and then 2 in this one, and then 2 in this one makes 14 electrons. And so our orbitals these are the orbitals that have electrons in them, and these are the different, or in other words, these are different energy levels that the electrons can exist in. Drawing this as a orbital diagram, like as a molecular orbital diagram, we have energy, energy increases as you go up, and we can draw our different orbitals. So we can put the 1s as the lowest energy, followed by 2s, 2p, 3s, 3p, and then 3d, 4s, etc. And let me label them: 1s, 2s, 2p, 3s, 3p, and so forth. Here, 4s, 3d. Okay. And we can fill it up. So there's 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, 2 electrons in 3s, and then 2 electrons in the 3p. Okay. And so this is the MO diagram for a singular isolated silicon atom. And you'll see how these other molecular orbitals, the electrons will never exist in the, or will never exist in these, or not never, but will not exist in these other orbital shells because they're higher energy and there's a lower energy for them to be satisfied in. Now, what happens when these silicon atoms start to bond with each other? Well, when they start to bond with each other, they're able to achieve lower energy states, which is why it's preferential for them to bond with each other. What happens is they become sp3 hybridized. And what that looks like in this diagram is the 2p and the 2s orbitals come together to form the 2sp3 hybrid, and the 3s and the 3p orbital come together to form the 3p s3 hybrid. And you can see how since there's 4 different orbitals, there are 1 2s and 3 2p, we'll have 4 2sp3 orbitals. Similarly, we'll have 4 3sp3 orbitals because there's 1 2s and 3 3p. 1 3s and 3 3p orbitals, meaning there are going to be 4 3sp3 orbitals. And so we can fill it up again. 1s, nothing happens to it, but 2s will have 8 different electrons. And 3sp3 will have 4 electrons, which occupy like that. And I didn't draw it very clearly in this diagram, but the sp3 orbital will kind of just like be at an energy level that's halfway in between the 3s and, not halfway, but in between the 3s and the 3p. Similarly for the, and for this reason, it's preferential for the silicon atoms to bond because it's able to achieve this slightly lower energy state. And it, of course, wants to minimize its energy state. And so then, once the isolated silicon atom becomes hybridized, then when they bond together, when the silicon atoms bond together, so let's say in this scenario, I did draw a tetrahedral structure, but let's say we're only looking at 2 atoms, then what happens is each silicon atom has an sp3 orbital, has 4 sp3 orbitals, and these orbitals can never exist in the same energy level due to something called the Pauli exclusion principle. So they differ slightly where they are, similar for the 2 sp3 orbital, which I'll draw like this, and similar for the 1s orbital. They'll exist in slightly different energy levels, but nonetheless have twice the number of atoms. So I'm drawing it out, all the different electrons. There's 8 electrons completely full here, and then similarly here we'll have 8 electrons, 4 from one atom, 4 from the other silicon atom that occupy this lower energy state, and then no electrons at an empty shell for this other energy state. So just walking through this again, this is the orbitals, this is what the electrons look like for the isolated atom. Then when a silicon atom has the opportunity to bond with another silicon atom, it becomes sp3 hybridized, which is a lower energy state for it, which it likes, and then combines with the other atom to form this molecular orbital structure. And when a lot of atoms start to bond together in a lattice shape, right? We can imagine, so lots of different silicon atoms start to bond with each other in a lattice shape. We can imagine that all their molecular orbitals have to go in slightly different places, leading to what's essentially just a continuous band of where the electrons can lie as an energy level, right? A continuous band up here, which continuous band here, here, and here, where this band is completely full, this energy band is completely full, this energy band would also be completely full, and this one is completely empty, right? Because they just start to form, each of these orbitals start to just like be in different locations. Similar to how like here the two different orbitals for the four orbitals for the 2 different atoms had to be in different places. As you combine a bunch of atoms, the 4 orbitals for the different atoms have to be in slightly different places, creating this, what's essentially on a macroscopic scale, a continuous energy gap. And I'll just write here, this one's empty. So analyzing this, and so this occurs for when you have a full lattice, right? Just to review one more time, this is when the energy level is isolated. Then when it wants to bond, it becomes hybridized, which is what is happening here. This is the molecular orbital when it bonds, and then this is what it looks like when it forms a full lattice. This is the band, this is what the energy levels look like. So we don't need to really look at these energy levels. Those are the core electrons, and they're pretty stable, so they're not really going to interact at all, like electrochemically or physically at all. So we want to focus on these upper 2 band gaps, of which we call this one the valence band gap, because similar to valence electrons, it's like the place where the electrons exist at the highest energy level. And then we call this the conduction band gap. Or sorry, not band gap, the conduction band, because when the electrons get to this energy state, they're free to flow around in the way that like conductor metals are able to have their electrons flow in like a mobile sea. In a similar way here, when the electrons are able to cross the valence and reach the conduction gap, they're also able to flow freely. And this space in between is called the band gap. It's a very important property for semiconductors. Okay, one more thing I should mention is if you're familiar with molecular orbital theory, you'll know that this like splitting of the orbitals into this empty space and this empty space and this filled section is called the antibonding molecular orbital. And then this is called the bonding because it's antibonding because it's a higher energy state, so it is not conducive towards bonding, whereas here this is the bonding orbital because because when electrons lie in this space, the bonding is actually reducing the energy level rather than increasing it. And so these antibonding and bonding molecular orbitals, when we see them on a macroscopic scale, they form the conduction band and the valence band, which is what we're talking about here. And the space between them, or the energy it takes to go from the valence to the conduction band, from valence electrons to free electrons, that space is called the band gap. Now, this model is helpful, but and it comes from using molecular orbital theory, but now we're going to see how we can describe this very similar process using kind of the idea of potential in Coulomb's law. So let's say instead we draw something called a potential well, which looks like this, for an isolated silicon atom again. So we have like our 1s and we have our 2s, 2p, our 3s, 3p, our 4s orbital, let's say. And then at the very top, is the ionization energy. The ionization energy level. Oh, there, ionization energy level. And then here's our different orbitals, which I can label as 1s, 2s, 3s, 3p, so forth. Or sorry, not 3s, 2p, and then like 3s, 3p. And the electrons exist in these different potentials. What I mean by potential is like the nucleus exists at the very bottom, right? And so the potential between the 1s and if you know Coulomb's law, you know that the potential is proportional to 1 over r. So that the potential of these electrons down here is very high, but then the potential up here is not as high. And when you get to the top, you get to something called ionization energy, which is basically the energy it takes for the electron to be completely free of the nucleus, bond from the nucleus. And it equals the the lowest conduction band energy subtracted by the valence energy band is equal to ionization energy. Or sorry, not conduction band. The energy of the electron in a vacuum minus the electron minus the energy it has in the valence shell. So now when we don't have just an isolated atom, and instead we have two different atoms of, in this example, I guess, silicon, then we'll have one potential well like this, and then we'll have another potential well here. I'll make it in a different color. We'll have a different potential well like this, with, their energy levels. I'm just kind of drawing them random, but still, you get the picture. And you see here how those energy levels overlap, where this is the first atom here, and this is the second atom. And they overlap in such a way that they minimize the amount of energy. And then finally, we can look at a bunch of these potential wells all together when they form a full lattice shape. And what it looks like is something like this, or you just keep going, but something like that. And there's kind of just this unanimous band that forms because they all have the same energy levels, like this. These different potentials. You can see it kind of forming with just two bonds, but you see there's this kind of unanimous gap. And so this kind of shows, what I think this shows is how the atoms' arrangements in the crystal affects the direction in which the energy levels occur, right? The reason I think this is a useful diagram is because it shows that, okay, when the atoms are arranged in this orientation, they have energy levels that exist in this orientation. And this is a very key idea that we're going to look at in a couple minutes, where the energy level of the atoms is decided by the lattice structure, the lattice constant. So to understand this further, we're going to look at this diagram that I have here of energy of the atoms as a function of the inner atomic distance between them. So this is sodium and this is silicon. Let's start with silicon, which is our semiconductor material. And you'll notice that this is the lattice constant, which is the distance that the atoms form from each other when they form a lattice structure. When the atoms reach this distance, they form these energy levels, which you can see right here, right? And then drawing the line, like right here. And so you can see this would be the conduction band gap, and then this would be the valence, or so not the conduction band, and this would be the valence band, and this would be the band gap. Compare that to something like sodium, which is a metal, where at the lattice constant, you'll notice that the band gaps overlap with each other. The bands overlap with each other, which is why sodium is a metal and why silicon is a semiconductor, because here they overlap the valence and the conduction, so that the valence band and the conduction band, so that the electrons can exist in kind of a free C mobile, whereas here it takes energy for the electrons to move to that mobile region where then they can behave as conductors. And so one of the things kind of to understand is like how these things are caused. So our atoms have these intrinsic atomic electron structures, which are determined by quantum mechanics, right? Where these molecular orbitals exist. But then these molecular orbitals, which are intrinsic to the atom, then when these atoms interact, the space that's formed apart between them, as seen here, which is the lattice constant, is decided by those intrinsic variables. And then also the band gap, as we saw with the MO, or the molecular orbitals models, is also decided by these intrinsic atomic electron structures, right? As we see. And so we can see that here, where the lattice settles and where the band gap energy occurs is completely decided by the intrinsic properties of the atom that you're looking at, whether it's silicon or sodium or some other material. Right? And so we looked at a metal and we looked at a semiconductor. Let's look at an insulator as well, just to see what the three differences are. So as I mentioned, metals, semiconductors have this energy band gap. Metals occur when the energy bands overlap with each other, which is what creates that mobile sea of electrons. Insulators occur when the energy gap is just humongous, to the point where it's unrealistic for any, you need to put a lot of energy in for any valence electron to move up to a higher orbital, to the conduction band, right? Showing how the intrinsic properties of an atom, the quantum mechanical properties of them, affect both the lattice constant, the distance, and the geometry of them, but then also the band gap, right? And I'll write that down actually. So the intrinsic properties of an atom, that is the fixed by quantum mechanics, which we'll look at in a second actually, cause both the geometry / like lattice structure and the band gap properties. The band structure and band gap properties. Now, we can understand this kind of this direction of causality a little further by looking at the quantum mechanics that I was talking about, right? So quantum mechanics is pretty complicated, but we're going to simplify it for the sake of the video to understand just what we need. Let's start with the idea. So electrons, we think of them as particles, but they can also be thought of as waves. And as waves, they have a wave function that describes them, which is just uses Euler's formula, right? A times the exponential of minus jk sub x plus some other constant, k sub 1, the exponential of positive j k sub x, right? So you have a wave moving to the negative direction and a wave moving in the positive direction, and so our electron can be described as a wave. And this function that I've written out here specifically is the wave equation for a free electron. That is an electron that isn't in an atom, right? It's just in a vacuum, right? It's just a wave described by Euler's formula. Now, let's look at the wave equation, or the wave function. Let's look at the wave function now for an electron which is in a semiconductor. Right? For wave equation for an electron that's in a for a wave equation, yeah. Sorry. Let's look at now the wave equation for an electron in a semiconductor. Here, so 5x, it looks very similar, and it's still a wave, but it's a wave that's being modulated by Coulombic forces, right, from the nucleus. Let me write that. It's being affected by Coulombic forces, and that's why we write the modulation function as u, because it's potential. It's the potential between the nucleus of the atom and the electron that's affecting the wave. And I will momentarily get to what k is here, what the variable k is, or the parameter k is, but here, so instead of just a simple wave equation, it might be like slightly modulated to look something like this, for example, right? This is just an arbitrary wave function, slightly modulated. Now, so to talk about k kind of has, in reality, k is the Fourier transform of the position. It's kind of a complex phenomena, but k can simply be thought of as electron momentum, as a kind of related to momentum. In fact, the formula for the electron's momentum is P equals h bar k, where h bar is Planck's constant divided by 2 pi. And so k can be in many regards thought of as kind of like a form of k can be thought of as a form of like momentum. And so when we look at this lattice structure, one of the things that we can say is that if u of k x x, if it's periodic as it is in this image, which it should be if we have a lattice structure, because if we have, all these same different atoms and they're forming a lattice, then the potential across any direction should also be across any lattice should also be periodic, because you have periodic atoms. Therefore, the potential from these same atoms should also be periodic. But if u of k sub x is periodic, then phi of x is periodic. The wave function of the electron is also periodic, right? And the wave function describes the energy of the electron. So it kind of describes the energy of the electron. And so phi of x is also periodic. And we say that phi of x has periodic. And we say that phi of x has Bloch form. And this is actually, what I'm describing right now is called Bloch's theorem. So phi of x represents, it's not exactly, but it represents the energy of the orbital, and it's dependent on both the wave function of the electron as well as the modulation caused by the nucleus pulling and having an effect on these electrons. Why this is useful to think about is that in a lattice, so let me draw a lattice again. In a lattice, right, we have these different directions of symmetry. Like we have the 101 101 plane that I was describing, which is this. And in these directions of symmetry, the wave function and the k values are, we can map a function phi to it, to these different like lines and planes of symmetry, which simplifies the way that we think about these electrons and how they exist in the lattice, and also connects the energy level, how the energy levels are connected to the lattice shape, because the directions that these energy levels form is related to the crystalline structure, as I mentioned above previously with this diagram. So the way that the atoms form together in a lattice in the directions that they do impacts the energy of the orbitals, which is described by phi. And we can further describe this with what are called band diagrams, or E versus K diagrams, right? Where we plot a certain direction of K and the energy over it, right? So, which is, again, kind of like phi of x, but not really. So, for example, let's say we want to look at let's draw an example of an E versus K diagram, one of these band diagrams, to understand them. So we have this. I'll explain what this means, but 0, 0, and let's say our band diagram looks kind of like this. Wait, hold up. So what I've drawn here, or I guess, okay, let me start with this. Let's draw the E versus K for a free electron, right? For a free electron, the E versus K, and we'll say K at 0 is here, is just a parabola like this, right? Kind of like the potential of a spring, actually. Right? It looks like this, where for very particular momentum values, we can have a particular energy value. E proportional to K squared, parabola. Right? But when we have electrons now that are interacting with nuclei and are in semiconductor materials and are not just free electrons, then our band diagrams look like this. And a simplified version of band diagram is like this, where we have two different waves which are periodic, and this bottom wave is the valence band, energy, right? And the top wave is the conduction band energy. Right. And we can kind of think about this, just as we did with the molecular orbital stuff, we can kind of think about this as like one band and another band. And the maximum of the valence band and the minimum of the conduction band make up, that difference is the band gap again. So in this diagram, you'll notice the minimum and the maximum don't lie at the same K values, don't lie at the same position. I should also describe what's going on with this x-axis. So you'll notice that the x-axis here, I should make these arrows instead of parentheses because they represent orientations. But so K equals 0 is here. When we move in this direction of the plot, we're going in the 1, 0, 0 direction, which is this way. Whereas when we move in this direction of the plot, we're moving in the 1, 1, 1 direction, which is this way, right? And so this portion of the graph represents the energy levels in this direction, whereas this portion represents the energy levels in this orientation. And so you can see how the min conduction band and the maximum valence band energy, or where the band gap occurs, it's an indirect band gap, because they don't occur at the same K value. This is actually what it's a simplified version of what the silicon energy levels, or silicon band diagram would look like. An actual band diagram is actually quite complex. I'll show you a picture that I had here of one here. You can see here it's actually quite complex, but we can but if we zoom in on a particular, and it's complex because, we have multiple orbitals. Like, this is probably like one band shell orbital, whereas like this is another band, and this is like another one. They're quite complex, and they're called noodle diagrams or noodle plots. But we can simplify them to just look at the parts that are important. the valence, which is a valence band and the conduction band, and the gap between them, and to understand what's going on. So this is an example of an indirect band gap. There's also, we can draw like a direct one where they're something like this, and this k equals 0. And gallium arsenide actually has this property of having a direct band gap, which is part of the reason it's used in LEDs. But this is the band diagram, which is so important to understanding the properties of semiconductors. And you can see how we built this up, and kind of just like how this diagram, this simple phenomenon and model of like energy orbitals is described in so many different ways when we look at solid state physics. So we can use molecular orbitals to describe the different bands and the band gaps. We can use this potential well concept. We can use wave functions and then band diagrams to describe kind of the similar idea of there being different energy levels where these electrons can exist, and if you provide energy, then they can jump to new energy levels and can become mobile, and which is why semiconductors exist in this middle ground of insulators and conductors. So we looked, throughout this video, we were looking specifically at the example of silicon and how it behaves, but you can try building up these same diagrams using something like gallium, right? Drawing out the MO diagrams and seeing what it looks like in terms of the conduction, valence band, or even try something like boron phosphate, right? Which is another semiconductor material, and you can see what it looks like in terms of these different bond diagrams to understand the unique properties of those semiconductor materials. I hope you enjoyed watching. Next video we'll look into current carriers and kind of fleshing out this E versus K diagram band diagram more fully. But I hope you enjoyed the video. If you enjoyed, like and subscribe, and thank you for watching.